you so much for joining. I'm really excited to have you all here today. My name is Ben. I'm an engineering manager here at Output. I work on the client engineering team. A special thanks also to Josh Hodge, the head of Body Programmer, for helping us make this happen. It's really exciting. I'm grateful as always. Over the past few years, we've shared much of our work through open forums with the developer community, and it's really important to us that we continue this practice of sharing. And so, to kick off the meetup today, Captain Dixon and Colin Sullivan, both staff software engineers here at Output, are going to be sharing a talk with us. And this talk is a culmination of multiple years of really hard work in software architecture. And I'm really excited for you all to see what they have to share today. We'd be happy to field any questions that you might have for us after their talk concludes. And after that, we'll have some time for open discussion. There are some light snacks along with refreshments back in our kitchen. If you haven't grabbed anything already, please feel free to. We'll have to close up our office at 6 p.m. today, so just be advised about that. But at that point in time, we'll head over to Frogtown Brewery, which is just about a block away from where we are now. We can walk over there together, just make sure nobody gets lost here. Yeah, I think that's about it on my side. Thank you all again for joining.
Yeah, thank you so much, Ben. Right. Yes, thank you so much, Ben, for inviting us to come out here. Ben and I have been friends for the past couple of years, and I'm very flattered that he would invite us to be here at Output HQ, who have been responsible for some very forward-thinking work, and I'm also very flattered that they've decided to share some of that here on the Audio Programmer. We know that some of the ideas that you put out have revolutionized what's happened in the industry, and that's more of what we expect in the future from Output. So thank you for sharing your ideas. We know that the developer community is very thankful to be able to have these insights and to be able to use those to create their own works. And with that, I'll go ahead and hand it over to Kevin and Colin. Thank you so much for your talk. And yeah, let's go ahead and get started. Colin. Woo!
Good morning, good evening. We're going to, as Ben mentioned already, we're going to talk about some of the application architecture we put together at Output, which few people in the room are familiar with already. And this is all about building lives on top of the C++ audio engine. First, some acknowledgments of our colleagues. In 2020, who's here, showed the foundation of all the work we're speaking of today at the Audio Developers Conference. In that talk, Spencer sets up really all the motivations for this work. Why build web UIs in general. And that has to do with the development process. The user interface tooling is very modern, well developed for web UIs, and the sort of cloud native idea where web UIs can easily reach out to web services. Also the collaboration between design and engineering. And Spencer also discusses how at Output we're maintaining a fork of the Juice web browser component, and that does things like enable developer tools and communication between the web UI and the C++ layer. I believe some of that is being built into Juice 8. And so we're kind of picking up where that talk left off. Also shout out to Arthur. In 2021 at ADC, Arthur mentioned some of the technologies we're using, and we started using them in production after Arthur was prototyping with them. And that talk also gets into design workflow topics, which are really interesting. So both worth checking out. So skip on. The first product output shipped with this web UI tech stack is a version of Arcade. It looks like this. This Arcade is Output's subscription product, which is an internet connected plugin in the DAW. It continually delivers new sound packs that are called kits. This is the browser screen where you can search through the sound library. So yeah, please check out Spencer's talk from ADC 2020 on YouTube to get a deeper dive into this. So at Output, we had the opportunity to set up a new project a couple of years ago, and an opportunity to consider the pain points and how things have been going thus far. So we're going to walk you through some of those architecture decisions we made in this new project and how it's been going for the past couple of years. So some of the pain points that we've been thinking a lot about, emergent complexity and bugs. This is sort of like an application architecture concern where a project grows and evolves over a number of years and the requirements change, and as the app grows we see bugs due to essentially complexity arising. Sometimes we talk about this as spooky action at a distance, where it's really just unforeseen complexity. Sometimes architectures like the model view controller and mediator patterns can be hard to enforce with tooling. We'll talk about this a little bit more. For example, one might need strict rules about what is a controller. Similarly, the mediator pattern can become difficult to trace kind of messages between components. Another class of issues is in the protocol layer. In particular, we found sending untyped messages is a pretty big pain point. So again, got us thinking how we could enforce this with tooling. And the last part is the messaging infrastructure itself. So we were able to send push string messages. But what about other things like binary blobs or kind of request response structure? And we'll get into these things. So let's take a look at the tech stack. The tech stack really hasn't changed since 2020. It's a great foundation for what we're doing. The work we're presenting today is really about how we're using this. Roughly we have the app and audio engine in a C++ app with Juice, and that is what hosts the web browser component. And you can see on the left there's two communication channels between them, and we'll get into that. And another thing that's important to note is the UI is all written in TypeScript now, and for anyone who isn't aware, TypeScript is a fully typed language. It compiles into JavaScript, and this has a bunch of benefits. It makes writing large applications less error prone, and hopefully allows C++ devs to have a little more natural experience writing the web UI code. So at Output, TypeScript is really the de facto standard now. All right, so Kevin, walk us through some of the application architecture.
Hey guys, yeah, so as we were starting this project, we were starting to think about what were some of the things we wanted to avoid that we had experienced in the past, and we're just going to look at an example of model view controller here as basically we had a lot of issues that we determined the root cause were due to the application architecture. So shown here is model view controller, which is one of the classic architecture patterns that we all know and love. And on paper, you get good separation of concerns. The controller can transform data from the model on behalf of the view, and then the controller can also set data on the model. So like when the user interacts with the view, the controller will figure out what changes to make to the model and then do that. And then the model and the view are like well separated from each other, so you get separation of concerns. The problem is that often this is difficult to enforce, and people devs start implementing kind of like desire paths between the view and the model, or things continue to escalate and you get all these localized view, model, and controller all kind of talking together, and it becomes really hard to reason about them because they are interconnected, and that kind of leads to the class of bugs that Colin was talking about, which is the spooky action at a distance. So yeah, we wanted to think about how we could fix that, and Colin suggested that we take a look at the flux pattern, which was popularized by Redux on the website. It's largely become the default for web applications these days. And yeah, so broadly, this pattern enforces data to only flow in one direction. So you have the store, which is sort of the immutable program state, and then you have the view, which is deterministically rendered from the store. And then if the user needs to affect change on the application, they can send an action to the dispatcher. So you can see that annotated here. Excuse me. And so what you end up with is this sort of unidirectional data flow is enforceable by tooling, because only reducers, which are a special class of like pure function, can modify the model. And they're deterministic. They take in the current state of the model, the user's action, and then output the next state. So it kind of just goes in this circular flow. So let's look at how that might work. On the left, we have a simple action. So we're dispatching the action of increment to the store. And then on the right side, we have the reducer code that just takes in the current state of the model, which probably contains an integer, and then we add 1 to it and return that new state. So the view or any other part of the program is not just saying like make the number 42, it's just saying whatever is currently happening by the time you execute this action, increment it by 1. So it's important to note that reducers are pure functions, they can't have side effects, so they're relatively easy to test. Yeah, so let's move on. Yeah, they're easy to test, easy to reason about, and the state, how this, the state is all changing in one place. So you can just kind of look through the reducers and like reason about the way the application is going to behave. Then yeah, so views, like I mentioned before, are deterministic for a given snapshot of the model. You should always be able to do like a clean render from the model and it'll always come out to the same result. The view isn't necessarily concerned about transitioning from one state to another, it just draws given the data that it has. Yeah, and then finally actions are critical. They inform the dispatcher like what the user's intent is. And it's really easy to see in code review. This is where like, if you can enforce it with a tooling, like is it easy to understand what your coworkers are working on? And generally the way that this structure works is it's really hard to break it and like circumvent it on purpose. So you kind of like, it's very easy to tell if somebody's doing something that's like out of the ordinary. And this kind of leads into our next part of the talk, is that actions are easy to serialize because they have very little data, and it makes a convenient format for communicating change between a distributed system. So let's look at how we have iterated on this architecture. So we showed the unidirectional data flow on the previous slide, and now we're getting into the meat of it. So we have the C++ application, which is doing all the audio processing, and then we have a web view. So the view is in fact the web UI that has its own entire flux setup inside of it. So it's the dispatcher, the store, and the view. But from the C++ application's perspective, it only has a store and a dispatcher, and then the web UI is the view. So basically, the C++ app is just responsible for communicating changes to the GUI, and then the web GUI can redraw itself Without getting too deep into it, the web UI has a lot of state that the C++ side doesn't care about, like, selected items or what panel is being shown. So that as this grew, we ended up putting the web UI having its own store, which is kind of a merger of the C++ store and its local data. And then the interesting thing that we could do with this is now that we have an audio engine, that's actually just another view on the model in the state of the app. So given the current state of the app, we can render an audio buffer that reflects that. And then the audio engine is also able to manipulate the state by sending actions to the dispatcher as well. Yeah. So this is kind of an example of like how the flow might go. The view, when the user takes action on the view, it can serialize that action and send it down to the C++ side. The GUI doesn't receive a state update until the round trip is completed, and the C++ store is updated and then notifies the backend. So some of that communication here is what Colin is going to fill you in on next.
All right, yeah, so this gets into kind of the transport layer, some of the details there we think are interesting to talk about. So the direct communication is what we call the ability to send strings, essentially, between the C++ and the web UI. And this is really where we started, and this is the same way the WebView and C++ have communicated since that first version of Arcade I mentioned was shipped with this technology. And so it sends strings. That's pretty much all there is to it. In the application code, it might look like this. Sending strings means we could send JSON messages. So let's dig a little deeper. We can look at how that is set up in the web app. You can see there these two method calls, window.receiveMessage and this window.webkit thing. Web devs will instinctively see this. Window.webkit is not like a standard API. When you're adding stuff to the window namespace in a web app, it's kind of like using a global variable or something. In this case, window.webkit is how the Safari web view works to inject this kind of message, this function that the UI can call to send messages back to the C++ side. In the output products, we're using the system-provided web views, so Edge and Safari. That's unlike the Chromium, it's unlike the Electron model, which ships Chromium in the app bundle. The output products don't ship the web engine. It just uses the system-provided one. So in Safari and Edge, they're a little different. This is how it looks in Safari. So this message is called, that's like the lowest, or this function is called to send a message, so it's like the lowest level. And on the C++ side, this is what things look in the native code there on Mac. When a message comes in, this did receive script message. Anyway, the idea is just that a message is coming in, it's a string, and outgoing, this trick is used to actually, it's just executing a string of JavaScript. It's just asking the web view to interpret this JavaScript string, which is generally considered to be like a dangerous thing to do. In this case, it works just fine because it's all contained in the code. It's only going to be executed by our messages. The main point here is we're sending strings between the C++ and the web view, and then it's provided to us from the system web view APIs. Okay, so let's talk about some of the work we've done on top of this. One challenge is, as I mentioned before, typing these messages. We're just sending raw JSON. Anyone who's set up a system like that might have found, you have to know what message you're sending. there's challenges with that sort of thing. Just knowing what message is coming in, what properties does it have, that sort of thing is a classic distributed systems problem. But on top of that, what about the developer experience? Like working with typed messages versus working with just raw objects and setting their properties and stuff. So first, let's talk about the distributed systems part. Just having a standard format of sending messages, so all messages are the same. This is how we're doing that. Message has a name and a payload, and so the name tells you what the type of message it is, and then the receiving end knows what the shape of the payload is. So in this example, a user info message has a user object with an email in there. And so this is just kind of like arbitrary setup. This is how we've done it. So now we know what kinds of messages we're sending. So now let's talk about the data types. Again, the UI code is written in TypeScript, and the C++ is typed language, of course. So we have this opportunity to have the fully typed objects on both sides. And so along the theme of trying to enforce these kinds of conventions in code, we looked into how might we automate this part of the code. We don't want to be like writing a type in TypeScript and then writing it again in C++, and then something gets changed in C++, you have to maintain the part of the TypeScript. So we've learned how to automate this part of the code base, and I'll talk through that. So we auto-generate the data types and strongly typed messages from a JSON schema. It's like the single source of truth, and it generates the data types as well as the message parsing code. QuickType and Loman.json. Loman.json is the JSON library in C++ that kind of comes with QuickType. It's very cool tools, and they could do really a lot of these things just off the shelf that I'm gonna show. And the workflow is roughly updating the schema files, running a generate command, and then the TypeScript and the C++ code files are generated. Okay, so quick example. Here on the right, we have a user info object. On the left, we have a user proficiency. Proficiency is like, where is this user in their musical journey? And so you can see on the right, there's the email and the name, and it links to their proficiency. So this data model can be, the objects can relate to each other. And the age is an integer. I don't know, I don't think that actually exists, but I wanted to get a number in there. The idea is we can have anything we need. We can have floats. I'm glossing over some details, but this is really the important bits. So now we're looking at the generated code. This TypeScript, proficiency and user info is generated. And because of the way TypeScript and JavaScript works, this is kind of all we need, because it could just be used. The top function, takes in a message and provides a user info message. It's kind of like a static cast in C++. There's actually not really anything to do, because we know what message there is. Of course, if it was wrong, that's a kind of a detail, but we trust that the C++ side is sending the web view, the message named properly, and so it's just like a kind of like a typecast. So on the bottom, we could see a user info message is received, and then it's converted from a raw message to a user info message, and then it's sent on to the next part of the application. And so the main idea here again is that all this kind of mess roughly is auto-generated, and the application code that software developers are writing is all working with the typed objects. Okay, and on the C++ side, it's very similar. A proficiency enum and a user info are generated, and then we do actually need a bunch of message parsing code to be auto-generated, and that's what this looks like. And this comes from the Loman JSON library. That's where that nice syntax comes from, but essentially this is all off the shelf from the QuickType tool. So yeah, now we have this auto-generated TypeScript and C++ code. It's really nice. We have customized QuickType a little bit. I'll just show one of those here. This is a factory method for creating a user info object with some default values. And auto-generating these is helpful for unit tests that need to work with these objects. Again, we don't want to be maintaining those as well. Imagine a new property is added to this object, and now all the tests are failing because that object needs a new property. So this factory would just get automatically updated, and then the tests would keep running. And yeah, just an example of like a test needs a user info. It doesn't care what values are in there. Maybe this test needs user info with a certain value set. That's how that might look. All right, Kevin's going to talk us through how some of the round-trip communication.
Cool. Yeah, so again, how do we glue all this together? Kind of at a high level, we're going to look at this example where based on the user info message we were just looking at, the GUI is going to dispatch an onboarding done message to the C++ side, which would then run its reducers, the store will be updated, and then some data change will be pushed back to the web UI. The web UI doesn't receive the new state until this round trip is completed, and then it redraws. So let's dive into this. Here's an example of what our our schema would look like that we were talking about. So on the left we have the proficiency that we saw before, which we're calling now the onboarding done payload, has a proficiency value. And then the onboarding done message itself has the message name that Colin was talking about to distinguish the type of message, and then we know the shape of the payload from that. Something to highlight here is another modification that we made to QuickType is to add something called context to the message that lets our tooling know if this message is being sent to the C++ side or if it's being sent to the GUI side. So if something is a from GUI action, then we add that to a variant that defines all of the types of messages that our C++ dispatcher will accept. Our journey starts here on the TypeScript side. We have the onboarding messages there. The user, let's say they've selected it from a drop-down or something. We can just put that as an argument here and then fire off the message. As you can see, sending messages from the TypeScript side is pretty efficient. It's just 2 lines of code to create the message and then send it. So one of our concerns was developer experience, how that would go. And then it's serialized, it hits the wire, as we showed earlier. And then what I was talking about is we use a library called logger, which is, flux and redux are kind of taken for granted on the JavaScript side, but on C++ it's kind of rare, so I wanted to dig into how this works. So there's a variant in this case. It could be a string or any type actually that you want for your action, but we wanted to use a variant so that we could have every action type contain data and be a little more structured than just a string. So with our code generation, we can add the onboarding done message to this public app action. The deserialized method that I show next is also auto-generated. We know that if it's a from GUI action, that it should be in this list of things that we can deserialize. And then this is manually written code at the bottom, the on receive message, but We just need to like determine the message type, deserialize it, and then call dispatch with the strongly typed variant there. Since it is a variant, we decided to do that. We use the normal std visit. As I was mentioning, we use the logger library from Juan Pedro Bolívar Puente. You should look it up, it's in our bibliography. But you then bind a free function to be the root reducer that takes in your model and the action type, and then it returns the next model. So this is how we enforce that contract of no side effects, only pure functions can be used here. So the next thing that happens is, like we were saying, we're using a variant, we're using the std visit, which requires the visitor to be exhaustive, that is, that it handles every type. So our auto-generated code, if you go and make a new message, it adds it to this variant, and then it's kind of like a dummy check. Basically, the C++ side won't even compile until you've implemented support for that message. So that's another way that we use tooling to enforce better quality code. So here's an example of how you might write the reducer. Again, it's a pure function. You take in the current state, you modify it, you return it. So we're going to handle this. We're going to set onboarding to finished, and we're going to set the proficiency to whatever they selected. And then finally, we're going to set the view to a new view. So the GUI can look at the enum, like what page should I actually be drawing, and then move forward out of the onboarding into the main part of the application. Something to point out here, the C++ heads might notice that we're passing state by value everywhere, so we're incurring the cost of copies. We are actually not. We're using a library called immer as well from the same author. He had a vested interest in implementing flux for C++. So immer basically gives you copy on write semantics to C++ objects, so it's not until you actually modify the object in the reducer that a copy is made. So you can basically pass these around as much as you want without really worrying that anything bad is going to happen. So this kind of helps you have this immutable data model with low cost on the C++ side. Excuse me. So the final piece of the puzzle here is, once we've updated the state via the reducer, how do we know that it changed, or how can we do that? And so this logger library also allows you to either look at the whole model or focus on a part of the model and watch it for changes. And then when that happens here, we can emit a view state changed message to the GUI, and that kind of results in closing the loop here. Yeah, so that's kind of the life cycle of a message. And so Colin's going to tell us about some of the new functionality we added to support transactional messaging.
All right, yeah. Earlier I mentioned how we're sending strings between the two layers, and it's a push. We call this our direct messaging channel. It could be, messages can be sent from either side, the web UI or the C++ layer. And so one problem with this is the transactional messaging is kind of cumbersome. You can see here a message is being sent, and then somewhere else in the code is where the messages are being received. So imagine like a database-like operation where if something needs to be created and then it needs to be used right after because it got a new ID or something. That's kind of hard to do here because you create a thing, but then you have to somehow track that you're waiting for the new thing to come back and the response somewhere else, and then, yeah, so that kind of thing, it can be cumbersome. And then I'll talk in a moment about how this is related, but another thing we cannot do with this system is sending arbitrary raw data. It's strings again, so I mean, we could base 64 encode something, but it's really not, JSON's not meant for just sending. What if we want to send a waveform or a graphic or something? So I'll talk about some of the solution we've worked out for this, but first let's talk about HTTP requests, as old as time itself. Here we can see HTTP requests being made in modern web code. It's using the fetch API. For anyone who is unfamiliar, this is a W3C standard. So this is not a third-party library. This is just like in a web browser. This is something you could do. Make an HTTP request to a server. This is a very natural thing to do for a web application. And the fetch API has JSON parsing built in. And HTTP is a request response protocol. So request is made, response comes from the server. Yeah. In our infrastructure, we figured out a way to intercept HTTP requests in the C++ code. So on the right-hand side here, you can see it's still making an HTTP request, except it's using this special scheme, output inc. And so what happens is these requests are intercepted by the C++ code, and they never go to the network stack or the server. So C++ is not running a HTTP server. It's using APIs from Safari and Edge that are listed there that enable the C++ code that's hosting the web view to intercept the requests before they get to the network stack. And so as a result, the request is essentially handled in memory and never hits the network stack, and it's very fast. So this is our solution for transactional messages. So we have some messages that use this instead of sending the push method, and that allows us to get a transactional kind of API from the UI to the app. And as a bonus, we found that this also works very well for sending binary data, because the fetch API also has this thing called array buffer. For anyone who's not familiar with that, it's another W3C thing. This is just like the modern way to work with binary data in a web browser. This doesn't, if you fetch some binary data from a server somewhere and in your web browser code, this doesn't put it into like a JavaScript list. You know, it's a native API into the memory buffer. So it works very well. Yeah, so this is what we are using as well for the UI to fetch binary data from the C++ side. And it's also very fast. And we did, of course, compare performance analysis, all these things. Should we base 64? Should we use the other, actually try strings? Nothing compares to this, which is really the most direct way we have right now for the C++ side to just transfer memory into the UI. So let's look a little bit at how that works. This is kind of what the C++ code looks like, which is kind of like how a web server would look. But again, it's not technically a web server, but of course it's operating like one, so the code tends to look the same. In this case, the UI is requesting a waveform from the app C++ code. So we can use our same message, auto-generated message types for the message itself, the request. And in this case, the response gets waveform data from somewhere, packages it up into output span, which could be replaced by native C++ span, C++20. And you can see here, it's doing very little. The idea is like just no copy until it hits the native API, and the Safari does what it does. Can't really control it after that. And so, yeah, again, it's very fast. There's almost no serialization overhead here. There's nothing really being serialized, just kind of pointing the web view at the memory buffer and saying to send that to the web UI. All right, so back to Kevin. Tell us about some audio engine stuff.
Cool. Yeah, so earlier we kind of alluded to the fact that the audio engine is just another view on the same data that we have in the C++ app. So how does that actually work? So here's kind of like a life cycle diagram. So when the audio, or rather when the application has a change in the state, it'll place it on a queue, lock-free queue headed to the audio engine, and then at the top of the render of the audio thread, it'll take a look at that queue, see any incoming events, which may include a new application state, and then using this render context, as we call it, we expose the current state to all of the children in the audio graph. So this kind of like enforces things to be a little more deterministic on the audio engine side, where people who are generating audio can only look at the current state in their buffer. So that kind of helps smooth things out. And then any outgoing events, like data that's been computed in the audio buffers, such as like VU meters or the playhead position or anything like that, can be pushed onto this outgoing queue, which is then processed by the dispatcher. So it's akin to any other action that the user might take, and that executes through the normal reducer pipeline that we were describing earlier. So here's kind of the start of that. Excuse me, yeah, so this is actually how that might work when we have a playhead update. The GUI thread will then process any messages coming back from the audio engine and then pushes them through the dispatcher there. And so it'll hit the reducer that can update the transport, storage, or anything like that, which then would get synced over to the GUI, who can update the position of the playhead as it goes. So that's kind of the broad strokes of the audio engine. And we wanted to sort of like, now that we've built all this stuff, how did it go? Some of our original problems at the outset were dealing with emergent complexity and bugs. And based on having all of these reducer functions that are pure and having very small components that are easy to reason about, we've had very few bugs due to components interacting. If the state changes and the object can deal with it, then it's fine. Like it's very easy to reason about even how to write unit tests in this case, because you sort of have a finite list of states that you even deal with. So that's been fantastic. Using QuickType to generate the serialization code and to keep everything in sync on TypeScript and C++, we've had actually 0 bugs in the protocol layer. And then finally, the messaging infrastructure, some of the improvements that we built there, we were able to build on top of our already successful direct messaging system to have both transactional messages and high performance messages. There's still like a couple things to work on here that, now that we've lived with the system for a while, any feature that is kind of like a vertical slice, I guess, through the stack that's both web and C++, you end up kind of generating a lot of boilerplate because you have to write the schema definition and then you have to write a reducer on both sides, and then anything around that, like the minimum cost to build a feature that spans both sides is a little more than in some systems. So maybe we'll just try to automate more of that code generation. We also learned that it's smart to decouple your file format from your protocol. So we found it really convenient to define all these objects in the protocol between the GUI and C++. So when it came time to generate a save file, for example, we just reused all the same structures because they're already in memory that way. It seemed easy to flush them to disk, but the needs of the protocol between the UI and the backend end up diverging from your storage needs pretty quickly. So that's been a pain that we'll solve. I think the quick and dirty answer is to just maintain separate schemas for both and translate them. And kind of the final thing that we're looking forward to is Microsoft allegedly, excuse me, is committed to shipping WebView 2 for Mac, so we could unify on which browser stack we're using, which would be nice to target only one, but it's working for now. So we really appreciate you guys coming through, and if you have any questions, we can field those at this point. Yeah, thank you.
There's someone in the room.
Yeah, I'm just curious more because it sounds like two browser capabilities is a big pain point for the project. So I'm sure you tried some sort of open source or open license browser along the way. What was the final decision to just keep Mac and PC separate in that kind of way?
Yeah, so I'll just repeat the question for the stream. And the question basically is like, why would you continue using two separate browser stacks when potentially you could do the Electron thing, which is ship a browser stack? And I mean, sort of the short answer is that, have you tried compiling Chromium Embedded Framework? Like it's it's sort of a nightmare. It's certainly possible, but after I don't know, I'm gonna like out myself as giving up here, but I spent like 1 or 2 weeks trying to compile it, and I was not even close. In Spencer's original talk, we actually forked the Juice web component, if you're familiar with that. So broadly, a lot of this stuff already worked, and we just grafted messaging onto it, and then now the URI stuff. So a little bit of it is like just taking like the fastest path to market. But there are some downsides, like on Windows, we have to ensure that we're delivering the Edge runtime in our product installers, for example. But by and large, I would say WebKit versus Chromium, like we have very little special casing in the web code. Just the state of web browser conformance is pretty good so far. So I don't know if you have more to add to that, Colin.
Yeah, most of the challenges arise where it gets into the operating system level. So things like keyboard focus bugs, or like, pastes, or like, things like that. That's where we hit most of our like Mac or Windows specific issues.
There's that like small embedded library too, right? What was the name of that? That's like an embedded web renderer.
We did do some testing with Ultralight.
Ultralight, that's right.
Yeah. Which is
Jules is really big on it.
I mean, it is pretty sick. I think one of the reasons we didn't select it, I mean, we did this eval 2 years ago, is that it's basically a one-man show. When at least in our company, we have some criteria for evaluating open source libraries, and the bus factor is real. I think we didn't want to, stake all that on there. And something we didn't get into in this talk is we were really interested in using WebGL to paint real-time graphics, which Ultralight didn't support at the time either. I think they have made progress on that, but yeah, that could be very cool. Yeah, Aaron.
Do I understand all of the plots are being sent back and forth through binary, call and response, or is there some additional side channel that's, bring me a preload of such and such, or refer back to it, or was there anything that you lost over there?
Do you mean with regard to large binary data?
Yes.
Yes. So the question is, how are we transmitting or referring to large binary data between the web UI and C++? So what Colin was showing is we can go back to that slide actually. Yeah, so here, the main thing that we're actually transmitting that's non-trivial in size is waveform data. You can check out Output Creator and see where we're drawing waveforms. And so it's essentially just downsampled PCM that we're transmitting. So yeah, it's not huge, it's a few KB, but it's enough that it would be annoying. And so here we're setting the headers in this response to application octet stream, which is kind of the universal web content type for binary data. And basically we just are taking an array of floats, casting it to bytes, and gluing it into the response. And on the JavaScript side, we do .array buffer, and then we just pass that over to WebGL and we can scale it or whatever, and it's essentially just reinterpret it as floats on that side as well. So yeah, basically, the thing to point out maybe is that the web process itself is running in its own process, so it has its own memory space. So you effectively have to copy the data across. To the previous question's point, if we use something like Chromium embedded or Ultralight, there's ways that we could modify those stacks to do like memory mapping or more complicated things like that, but that's a exercise for the future, I guess.
Yeah, one thing to maybe to clarify this here, from the UI's perspective, it thinks it's asking a web server. The UI doesn't know that this URL endpoint is special. So from the UI's perspective, it's just like it's fetching an image from a web server, fetching from a server in the cloud that's giving a binary blob back to it. But of course, it happens much faster than any server could deliver something to it because it never goes into the network.
Does this only go one direction then, or could you do a post and send from the web to the C++ side?
That's a good question. For this binary stuff, so the setup I was speaking about before where we can send strings, that we could push from either direction, and that happens regularly to send kind of the application state. For this binary stuff, the web view really needs to ask for it because it's modeled like a web server. I think there are ways to do that, but we don't. Yeah.
I mean, we do actually post. We do have some post requests, but we're not doing it with binary data. It's just a couple situations where we have like really big blobs of JSON that we need to push down there. So the system is capable of it, but I think, it's not. It would be more of a straight copy rather than. I think when you call array buffer, it's like a proxy into the C++ array. So in theory, if it's optimized to pass that into WebGL, it could be going straight to the graphics driver. I really doubt it is, but it could be.
Cool.
Yeah.
Yeah, Josh.
Yes, we have a couple questions from the live chat. One is, how are clocks and MIDI handled?
Okay, yeah, so we have the question from the stream, which is how are clocks and MIDI handled? And so all of the audio engine is actually in C++, so we're the usual normal caveats of latency, but not very much. It's all using, honestly, just juice under the hood to receive and output MIDI, and same with audio. And so I think the interesting thing to recognize here is that the UI is inevitably about one frame behind the audio engine. So when we're sending these, for example, we have this example about the playhead moved event. So that's emitted at the end of an audio buffer, pushed down into the GUI, or well, I should say into the main thread. It's processed, it's added to the store, and that probably takes, that's driven by a 70 hertz timer. So that's already however much latency that is, about 10 to 14 milliseconds or whatever. And then on the next GUI tick, the model will have been observed to have changed, and it'll push that message into the queue headed towards the web browser. And then I guess that gets, this is now Colin's domain of like how that exactly happens, but the measured latency there is about on the order of like 1 video frame, potentially 2.
Yeah, playhead is definitely like one of those things that ends up being a special case in the UI, because that's the thing that's like moving really fast and has to, tightly follow the app. Yeah, to Kevin's point, though, the rest of the high performance, like real time concerns really are happening in the C++. And the real-time graphics, like scrolling and things like that, is just happening in the UI, and that's, these are separate processes in the system.
Got a couple more questions. Is there a latency difference between a button using your web UI versus doing that natively with Juice?
Yeah, so the question is there a latency difference between this UI stack versus the Juice UI stack? I think the answer is about 1 frame. If we've measured that, it's actually kind of an interesting thing that you might want to go down your own rabbit hole on. I'm most familiar, honestly, with iOS's input stack, and so there's like the glasses like touch sensor refresh rate. That's kind of the first tier of where that happens. If I remember correctly, basically by the time your app redraws in response to it, you're already about 3 frames later. Our system is essentially on par with that. JavaScript enqueues these messages immediately, and then it's the next Juice message tick that reads this queue. Those events get pushed into your normal application queue. So on Windows, it's like the WM message queue. On Mac, I forget the name of it. But the NS application, timer, whatever. So there's, most of that stuff executes pretty immediately, but there's, yeah. So I think, yeah, sorry, to zoom out, it's about one frame longer than normal.
And how much bigger is the resulting binary of using this stack versus a native Juice stack?
So the question is, how much bigger is the resulting binary? So on disk, it's like the same, more or less. I think the compiled web application is 10, 20 megs, something like that.
Yeah.
I think one of the performance costs that we actually run into is once you start running this distributed system, you have the memory overhead of the JavaScript runtime along with whatever memory you're incurring on the C++ side. So especially when it gets into things like copying waveforms, where they exist in both the downsampler cache on the C++ side and the web UI, you start getting duplicated memory. So there's some inefficiency there for sure.
Yeah, on disk, this relates to how we're using the system web view as opposed to like Electron. When you use an Electron app, it packages the whole Chrome, essentially. It's like you're shipping Chrome with your app. And we don't do that. Once it's opened on a Mac, the operating system provides the Safari web view to it. That's similar to how a web view in iOS works as well.
Yeah.
I'm interested in slightly more complex animation, like let's say you wanted to do portals X, Y pad with the circles. Could you do all of that in the web, no problem, or would you need to make some sort of a C++ procedural animation algorithm and then send all the information out?
Mm-hmm. Yeah, the question is, can you do more complex animation on the web, akin to Portal, one of our other plugins? I think actually one of the deciding factors in doing a web stack at all was how much easier it is to implement animations. Part of at least with earlier versions of Juice, it was definitely complicated to move objects smoothly on screen. There were just Juice components, for example. For our high performance stuff, if you look at Output Creator, the timeline is all rendered using WebGL. So we're using the canvas element there. We're using a library called Pixie for that kind of helps with drawing and converting to the WebGL code. And yeah, anything's possible with that. We did a proof of concept of drawing an FFT of the output at 60 frames per second. So we were doing an HTTP request, this intercepted one, every frame and drawing the result, and it ran perfectly fine. So I think anything's possible.
Yeah, I think there's Well, the WebGL, of course, is like on its own. If you just want to like run a crazy animation, that's going to be fine. But then there's like, are you drawing something from the audio engine? Because now you have the communication layer has to be high performant as well. And with some of these techniques, you can't achieve that. Yeah.
Cool. Yeah. Cool. Thanks for coming, everybody. Yeah, I appreciate it.
Yeah. All right.
Yeah, I don't really need this anymore.
Yeah, thank you so much, Colin and Kevin. That was excellent. Excellent talk. A lot of interest online, and just want to thank once again Ben and the Output team for having us here and for inviting us here. This is fantastic. I hope this is one of many more. Next month we're going to be in London with Queen Mary University. We're doing a hackathon with them, so we're going live from London. If you're interested in this type of discussion and you want to learn about audio software development, we have a community where we have over 10,000 members. You can join via theaudioprogrammer.com/community. We also have a book, so if you're interested in learning about how to create your own synthesizer using C++ and Juice, you can find out. The link is in the video description below, and you can get that book as a physical book or as an ebook. And with that, I'll pass it over to Ben for some final words.
Cool, thank you, Josh. Yeah, thanks, Colin, Kevin, once again. Really, really thankful that you all offered to do a talk here. And I'll see you again, Josh. Thanks for helping make this happen. Yeah, we're for those who are joining us in person, we've got some refreshments and snacks in the kitchen behind you. So after this, we'll have some time to just chat and have an open discussion here. And just as a reminder, we're going to be closing up shop here at 6 p.m. and heading to Frogtown Brewery, which is just a block away from us. So we'll walk over there together at that point in time. For those joining on the stream, thank you so much for viewing. We're gonna go ahead and wrap up now, but as Josh mentioned, please join his community. It's a very good place to learn about software development in the world of audio. Thanks, everyone.
All right. Great. Thanks so much.